In this video, we're going to apply the definition we just derived for computing the directional derivative. Again, an important criteria here is that we start with a direction that we're interested in, and that direction is represented by a unit vector, a length 1 vector. Then that calculation of the slope of the surface at the point AB in the direction of some u is going to be given by the x partial derivative times the direction u1, or times the component u1, plus the y derivative times the component u2. Note, we do not define directional derivatives for non-unit vectors. If someone hands us the wrong kind of vector, one that is not length 1, say for example v, we have to correct that first, and that's easy enough to do. If someone hands us a vector v that's not length 1, then we simply divide by its own length, and that'll make it length 1 while keeping the direction the same. And then we go ahead and compute with that reduced or enlarged vector that we need to specify all the ingredients in our formula here. All right, let's give this a try. Here we have a surface, we have a vector given to us, and we are going to calculate the slope of that surface at the point 2, 2 in the direction given by that vector. Our first question is always going to be, is the direction that someone specified for us, is it actually a unit vector? Take a moment to consider that, and then we'll check in. Well, looking at the u value, that's all that matters here. It absolutely is. This is a classic 3, 4, 5 triangle, or we can do the calculations. The length of u is the square root of the first component. That's what we would call u1 squared plus the second component, which we would call u2, also squared and square rooted. If we evaluate that, we're going to have 9 over 25. And on the second term, we're going to have 16 over 25. And that gives us the square root of 25 over 25, which is simply 1. So u is in fact length 1. It is a unit vector. We then proceed to find all the values that are required, going back a step, to compute the directional derivative. So we'll have the slope, not just the slope in the x direction, but the slope in the x direction at the point of interest, and the same thing for the y slope at the point of interest. Let's get calculating those. The x slope for this function here is defined by the derivative with respect to x, so 2x minus the derivative of x is 1, and the y squared is a multiplier, it stays around. Going back to the original function again and finding the y derivative, we have 0 for that first term and minus 2xy for the next term. Follow up, we evaluate those at the point 2, 2. And that's going to give us 4 minus 4, that's 0. This is going to give us minus 2 times 2 times 2 is minus 8. And just as a moment to reflect, this tells us that if we were to move in the x direction, we would see 0 slope, at least at this point. And if we were to move in the y direction, we would see a negative slope. The surface would be going downhill if we move in the positive y direction away from the point 2, 2. Our u1, we mentioned that earlier, is the first component of our u vector, and our u2 is the second component. So that makes the calculation of this directional derivative relatively straightforward. We take the x slope, 0, that is our x derivative at the point 2, 2, and we multiply that by 3/5, which is our x direction component. And we add the slope in the y direction at the point 2, 2, that's our fy at the point of interest, and we multiply that by negative 4/5, and that gives us the value of u2, the direction, the y component of the direction we're traveling in. And now we're ready to compute that. This is 0, and we end up with positive 32 over 5, which is 6.4. Now what that's telling us, we can be described in a full sentence. From the point 2, 2, that's where we are, in the direction of 3/5, negative 4/5, which would be really 3, -4 if we just think about it as a direction. It's positive x and negative y in this ratio. We would see the surface has a slope of positive 6.4. Leave out the positive. It has a slope of 6.4. For every small step that we take in the direction of this vector, we would see that we're going uphill at a rate of 6.4 up for every step that we take in that direction. In other words, all the classic derivative information, but now because we have different directions we can move in, we have to specify a lot more to be able to do the calculations. But the calculations themselves are relatively straightforward once you get the pattern of it. And remember that this pattern ties back to and looks a lot like the linearization formula. This is not coming out of nowhere. It's actually the same kind of formula based on the same kind of underlying logic. So don't get overwhelmed by the number of expressions you have to memorize. A lot of them are very closely related to each other. A follow-up question that we can ask is what happens if we go in the opposite direction? So let's imagine this again quickly as an x direction and a y direction. We're at the point 2, 2 as our starting place, and we were going in the positive x, negative y, so our vector here was u before. And if you imagine the surface over top of that, we found that slope was equal to 6.4. So if we travel in this direction, we get a positive slope. We would be going uphill with a slope of 6.4. Well, what if we make a new vector that's the negative of u? Well, that would simply be negative 3/5 and positive 4/5. So the opposite of this vector. And if we drew that, it would look like this. Up that way. That's our w. And the calculation would be almost identical. In fact, we have all the ingredients. We would take our, going back a page here, we would take our x derivative at the point, our y derivative at the point. Those did not change. So let's actually put those in first. Our -8 and our 4. What would change is we would include the x component now of this new vector, 3/5, and positive 4/5 here. And actually, if we go through the calculations, what happened is every ingredient in this calculation changed sign. So we end up with negative 32/5 instead of, in the last case, positive 32/5. So all we did was flip the sign. And what that tells us is the directional derivative in the direction of w of the function at the point 2, 2 is going to be the opposite slope. Same magnitude, but flipping the sign. And all that's capturing is our intuition, which is if we take a small step this way, we would see a slope of 6.4 uphill. If we turned 180 degrees and went the other direction on the map, we would encounter a slope of exactly the same magnitude, 6.4, but going downhill, as indicated by that negative sign. And that captures, again, our intuition about what would happen if we take really small steps. And again, if we imagine ourselves on a surface and look in one direction, imagine a small step in that direction, what would happen if we turned around and went the other way? We should expect to see this kind of symmetry.